Up next is how information flows through a neural network. Okay. Of course, the simple answer to that is forward propagation. That's how information flows through a neural network. And we'll see applications and prediction systems. And so our learning objectives here will be to be able to explain how information flows through a neural network, be able to define forward propagation, understand the mathematical computations performed in each neuron, perform forward propagation manually, implement forward propagation using Python, explain the role of activation functions, describe how neural networks make predictions in real-world applications. Well, before now, we've talked a lot about back propagation, which has a lot to do with chain rule. And the idea of forward propagation is for prediction, while backward propagation is for correcting errors in predictions, as we're going to see as we move on in this both in this particular video and on the playlist in general. So artificial neural networks, ANNs, are computational models inspired by the biological nervous system. So, I mean, the idea of neural alone tells you about the brain and all and its connections. So, artificial neural networks consist of interconnected processing units called neurons, and they are organized into layers. So, a neural network processes information by passing data from the input layer through one or more hidden layers to the output layer. So, to demonstrate that, right, you have an input layer right here. So you have an input layer, and then you have an output layer, input layer, output layer. But then in between this, you then have several connections in between, that then leads to this output right here. Okay, so so these are hidden layers then, hidden layers. So that kind of thing. So you have an input layer through, then you have hidden layers, then the output layer. The movement of information from the input layer to the output layer is called forward propagation. So from input to output, you have forward propagation. Now, forward propagation is the prediction phase of a neural network. During this phase, the network uses previously learned parameters like weights and biases to generate predictions for new data. And the information flow is always that you have the inputs layer and then you have the hidden layers, as many as possible, and then you have the output layer. Unlike backpropagation, no learning occurs during forward propagation. So in forward propagation is going towards prediction, and learning occurs at the phase of when we talk about back propagation rather. So forward propagation for prediction, back propagation for learning. For correct learning is about updating the prediction based on the error observed. Now, forward propagation, the definition, forward propagation is the process of computing the output of a neural network by passing input data through every layer until a prediction is obtained. So it goes through every layer. So you have the input and goes through every layer and then you get an output. That is forward propagation. At every neuron, two operations are performed. First of all, you compute a weighted sum of the inputs, which you already are used to. Talking about the weighted sums, right? That's WX plus B. Then you apply an activation function. We also did that. In the last video, we talked about why neural networks need nonlinearity, because of course, nonlinearity captures more nuanced behaviors of whatever data you're working on. So the output of one layer becomes the input to the next layer until the final prediction is produced. Mathematically, you have the inputs, you have the weighted sum, you have the activation function, and then you get an output like that. So this activation function state now, it can now be several layers. So we talk about the structure of a neural network. A simple neural network consists of three major layers. You have the input layer, which receives the input features. You have the hidden layers, which extracts patterns and relationships from the data, like what I showed right here. So you have inputs, you have outputs, but then you have the hidden layers in between, like that. So you have the output layers, which produces the output layer, which produces the final prediction. So the hidden layers extract patterns and relationships from the data. So imagine this, that you have input layer, X1, X2, X3, and then you have the hidden layers and you have all the transformations happening there with H1, H2, H3. And finally, you get the output layer, which gives you the prediction at that phase. So information always flow always flows from left to right during forward propagation. So in forward propagation, information flows from left to right. So uh this is okay. This is forward forward propagation, forward propagation with information flowing from left to right. So, and the end result of that is a prediction. Okay. But then, as we're going to see later, or we've talked about it a couple of times, even talk about back propagation, back propagation. So, for back propagation, the end result is going to be learning, that is, tuning of the parameters for better prediction next time. So, you have this uh series of forward and back propagation until you get the desired result. So information always flows from left to right during forward propagation, whereas it flows from right to left during back propagation. And like I said, forward propagation is for prediction, while back propagation is for learning. That is fine-tuning the parameters to get better predictions. Now, components of forward propagation. Now, suppose the neuron receives the following inputs x1, x2 up to xn. Same thing we've been doing all along. So each input has an associated with w1, w2 up to wn. Then the neuron also has a bias b. So the neuron first computes a weighted sum z equals x1 w1 plus x2 w2 plus x3 w3 all the way to xnwn, and then a bias is added to it. So the weighted sum is then passed through an activation function, a, which equals fz. So this f now can be linear, it can be non-linear, it can be, and types of activation functions are things like ReLU, that rectified linear, uh, rectified linear unit, I believe. And then you have sigmoid, you have Tanh. We mentioned Tanh in passing before now. And then you can also have this step activation function. So here Z is the weighted sum, A is the neuron output, and then F is the activation function, which can be any of the things I itemized already. Then we talk about step-by-step forward propagation now. Imagine we have X to be 2, 3. Weights are 0.5 and 0.8, meaning that the second parameter, the second input is weightier than the first, because the weight attached to 3 is 0.8, while the weight attached to 2 is 0.5. So it means 3 is more important in the scheme of things compared to 2. And then you have a bias of 1. So compute the weighted sum. You just have 2 times 0.5 plus 3 times 0.8 plus the bias, which is 1. So you have 2 times 0.5, 1. 3 times 0.8 is 2.4 plus 1. So 1 plus 2.4 is 3.4 plus 1, 4.4. Now you decide on an activation function, which is by default we use the rectified linear units. So using the ReLU activation function, you have ReLU z, which is the maximum of 0 and 4.4. Since 4.4 is bigger than 0, the answer is going to be 4.4. So the output of this neuron becomes the input to the next layer. So if for hidden layers now, maybe you now have other activation functions. So you keep passing it through all these layers like that to be sure we get the desired result. Then let's talk about matrix representation of forward propagation. Instead of processing neurons individually, neural network neural networks use matrix operations. So matrix are really so handy. So let X be 2, 3, for instance, and weights are 0.5, 0.2, 0.8, 0.6. And then the bias, you have B to be 1.1, to be 1, 1. So in an instance, right, the weights are 0.5, 0.2. In another instance, the weights are 0.8, 0.6, like that. So the weighted sum can then be computed as Z equals WX plus B. So the activation function is then applied. So you get A. Now we are talking matrix now. So that's why it's no longer small a like what we had before. So here, we had a small a right here. But now we're talking in terms of matrices. The A becomes big A because this A now is a matrix. So using matrix multiplication allows neural networks to process thousands or even millions of neurons efficiently. So, in fact, we discover that the whole idea of coding is based on the idea of matrices. So you can represent things as arrays and vectors and all of that, and then you can deal with many things at the same time. Now, forward propagation through multiple layers now. Consider a neural network with two hidden layers. So for the first hidden layer, you have Z1, which is W1X plus B1. So first activation function, you have A1, that's F of Z1 here. And then whatever the A1 you get here now, it comes to the second layer where you have Z2 equals. So this activation function here could be maybe ReLU, and then you come here and you do whatever. Maybe you do sigmoid, and then you come to the next layer and you have another kind of activation function altogether, maybe Tanh or something, depending on whatever you're dealing with. So for the second hidden layer, Z2 is W2 multiplied by the activation value you got from here plus the output you got from from the input layer, and then you have A2. So you apply the activation function the second time you have A2, which is F of Z2. So this A2 then becomes input for the output layer because we have just two hidden layers. So for the output layer, Z3 is now W3 A2 plus B3, and then Y cap, the final prediction is now another activation function applied to Z3 here, and this process continues until the final prediction is produced. So if you have more than two hidden layers, then it keeps going until you finally get your output. Now, talking about activation functions now, activation functions introduce non-linearity into a neural network. So without activation functions, multiple layers would behave like a single linear model. All right. So common activation functions can include sigmoid, where you have sigma of z equals 1 over 1 plus e raised to minus z. And then you have the output range. So of course, like we established this, I think in the last video, the one before that, that for a sigmoid function, the theta of z is always between 0 and 1. At minus infinity, for instance, at minus infinity, you have 1. At plus infinity, you have zero. So at say at zero, for instance, you have at z equals zero, you then have this to be 0.5, like that. So minus infinity to infinity, like everything lies between one. So that's for sigmoid right there. So these are activation functions. Another activation function will be the rectified linear units, ReLU, which just takes the maximum of zero and whatever z you supply to it. So examples include ReLU minus 4, which is 0. That is because 0 is bigger than minus 4, so the answer will be 0. Then ReLU 6, 0 and 6, 6 is bigger than 0, so the answer is 6 in that case. So ReLU is the most widely used activation function in hidden layers like that. It is the default, except otherwise stated. Then you have the Tanh activation. So for the Tanh activation now, that's e raised power z minus e raised power minus z all over e raised power z plus e raised power minus z. So the output range is this that the tanh of z always lies between minus 1 and 1, and it is some kind of saturation function. If I can show an example here, let's see. Let's go to decimal so you see how these activation functions compare. um okay, so if we do sigmoid, that is 1 all over 1 plus e raised to power minus, of course we have to use x here, so see what sigmoid function looks like. But for tanh, so imagine we have tanh x. So you see tanh x. So they look a bit alike, right? Except that tanh has a wider range. Tanh varies from minus 1 to 1, while tan is from 0 to 1, like that. So let me see, can I do ReLU here? ReLU is just the maximum of 0 and x. How can I pull that off? Let me just try. Is that possible? Max of 0x. I doubt it. Oh, really? It's working. Okay, yeah, now that's interesting. So you see everything negative. You see on the negative side now for the maximum, right? Okay, let me center this a bit. So so this is ReLU right here. For ReLU, everything negative lies on zero. But then on the other values, every positive value goes, it goes that far up there. So but if you want some moderation, you have tanh and sigmoid like that. So those are activation functions right there. Then we have softmax. Softmax is for outputs now. So for outputs, you have, let's say you have outputs 2, 1, 0.5. Softmax converts them into probabilities such as 0.63, 0.23, and 0.14. Of course, how it does that is that it takes, you have the exponent of 2, for instance, and you take the exponent of everything, and then so you now, and you sum up all the exponents, and you take the exponent of 2 over the total, and you get all these probabilities. So of course we know probabilities always sum up to 1. I think we've dealt with softmax in previous situations. So let's take examples to drive home the point about all of these things. Now, a neuron receive inputs, x1 is 4, x2 is 5, and then the weights attached to x1 is 0.2, the weight attached to x2 is 0.7, meaning that x2 carries more weight than x1, and then the bias is b equals 1. So using the ReLU activation function, we compute the weighted sum first of all. So we have z equals 4 times 0.2 plus 5 times 0.7 plus the bias, which is 1. So 4 times 0.2 is 0.8. 5 times 0.7 is 3.5 plus 1. So if you add all of that, this is 4.3 plus 1. So you have 5.3. If you apply the rectified linear units, then you have ReLU of 5.3 to be 5.3 because between 0 and 5.3, 5.3 is bigger. So the output you get in this case is 5.3 using ReLU. Now you have example 2. Let's use, in this case, we're using sigmoid function. I hope it's the same. Okay, well, I wish it had been the same, but it's okay. You can just try the same thing on different. Uh, in fact, I think I want to try the same thing for both, right? So here, mm, okay, well, I think there's no problem. If So I'll do this normally, and then if we had the same 5.3 for sigmoid, so that means you have like so with that we have e raised per minus 5.3 up here. So that would be 0.9, and that's 99.5. Whereas ReLU gets you, so that's 99.5, right? For this 5.3, like that. So let me put back the X there. Okay, so example 2 now, you have input 3, 2, and with 0.4, 0.5. So 2 matters more than 3 here. So then the bias is minus 1. So if you use the Sigmoid activation function, so first of all, we calculate the weighted sum, 3 times 0.4 plus 2 times 0.5 minus 1. So this is 1.2 plus 1 minus 1. So this is simply 1.2. If you apply the Sigmoid function, that is sigma 1.2. So that means that where you have x there, you put 1.2. So this is 1.2, and that is 0.7685, 0.7685, and that's exactly what we have here. So the network predicts a probability of approximately 76.85%. So there's a 76.85% confidence that the right prediction will be made in this case here. Now, what if we have a two-layer neural network given x1, 2, and the weights are 0.5, 0.3, 0.2, 0.8, and the bias is 0, 0, which is a Coulomb vector, and W2 now is 1 minus 1. So W2, of course, since we have two-layer neural networks, so the weights here are now 1 minus 1, and B2 is now 0. So use ReLU in the hidden layer now. So you're using ReLU in the hidden layer. So for the first layer, we have Z1 to be W1X plus B1. So W1X will simply be, so first of all, W1X will be, so that is 1, 2, 1, 2, and we put 0.3 over it. So first one will be 0.5 times 1, that's 0.5, plus 0.3 times 2, that'll be 0.6. So 0.5 plus 0.6, that's 1.1 here. Then 0.2 times 1, 0.2, 0.8 times 2, 1.6. So 1.6 plus 0.2, that's 1.8 here. And of course, you have the B1. B1 is 0, 0, so it doesn't change anything. So we still have 1.1, 1.8. Then if you apply ReLU, so applying ReLU now, you have A1 to now be, so if you apply ReLU, so for the first one, you have 1.1. So 0 and 1.1, 1.1. 0 and 1.8, the bigger is still 1.8. So that's the first layer. Now the output layer, we still have to apply ReLU, right? So Z2, you now have W2 of A1 here plus B2. That means our W2 already, we have that to be 1 minus 1. So that means that's 1 times 1.1 plus minus 1 times 1.8. So 1 times 1.1 is 1.1 minus 1.8. So you have minus 0.7. And if you compare, uh, so that's the output, right? So if we had to pass this through ReLU again, would have got 0, right? But this gives minus 0.7, like that. Yeah. So I think we have to be sure. Do we have to apply? Okay, having done this, I think we should apply it through ReLU again. So if you take it through ReLU, it means y cap is going to be 0 here. but the raw value of Z here is 0.7. So I think it's important to apply ReLU. So so that at the end of the day, Y cap will have to be the ReLU of 0.7, which is simply equal to 0. That'll be the final prediction in that case, like that. So we get 0. Okay. It's outside of the box now. Okay. So this should still be boxed. Yeah, so that's all we have now. So if you take the value of minus 0.7, because this is negative, 0 is the answer. Now let's talk about forward propagation algorithm. So the forward propagation process can be summarized as follows. First of all, receive the input vector, multiply each input by its corresponding weight, add the bias, then compute the weighted sum like that, apply the activation function, whether it is ReLU, Sigmoid, Tanh, and all that. Then you pass the output to the next layer, repeat until the output layer is reached, and produce the final prediction like we just did now. So then we have applications of forward propagation in prediction systems. Now, forward propagation enables neural networks to generate predictions after training, like we've been seeing. Like, I mean, we've been doing manual ones, but in the real setting, it's actually going to be more serious than that because you have tons of data there and tons of information, tons of inputs to deal with. Some important applications include medical diagnosis. You maybe input things like age, blood pressure, cholesterol level, blood sugar, and then the prediction is the probability of a heart disease is 0.93, depending on those values. I mean, in a specific situation, right? When you talk about house price prediction, maybe you have inputs like number of bedrooms, floor area, house age, location, and the predicted price then becomes $365,000. Then you have image classification. So you have output probabilities like probability of cat 0.85, probability of dog 0.10, probability of horse is 0.05. Then the predicted class is cat, like that, because the probability is that high. Then for email spam detection, so you just say, okay, based on the particular features of the email, probability that it is spam is 0.97. So you have forward propagation doing all of that. Then for rain weather prediction, so you predict rain with probability 0.8. So based on certain parameters or based on certain conditions. Then financial fraud detection. So probability that a particular transaction is a fraud is 0.98 based on whatever information you supply. And then we have recommendation systems. So predicted recommended scores. Now you have movie A with 0.91 probability, movie B 0.52, movie C 0.18. So the system recommends movie A because that's the highest predicted score. So that's how you get to see certain videos showing up for you on YouTube based on I mean, they take your behavior, the kind of things you watch to tailor the kind of what to give you the things you might be interested in, like that. So in summary, we see that you're talking about forward propagation, which is how information flows through neurons. Forward propagation is the process by which information moves from the input layer through hidden layers to the output layer of a neural network. So each neuron performs two main computations. First, you compute a weighted sum z equals wx plus b. Then you apply an activation function a equals f of z. So the outputs from one layer become the input to the next layer until the final prediction is generated. Forward propagation is the foundation of all neural network prediction systems, including medical diagnosis, image recognition, recommendation systems, spam filtering, weather forecasting, and fraud detection. So while forward propagation computes predictions, the network learns its weights through backward propagation, which adjusts parameters to minimize prediction error. So just like I said, forward propagation is for prediction, while backward propagation is for learning. And learning means fine-tuning the weights, fine-tuning the weights to ensure that the right results are obtained, fine-tuning the way to make sure that better predictions are made. So forward propagation for prediction, backward propagation for learning or recalibrating predictions for parameter tuning. All right, so let's talk about some practice problems here, like I always promised. So here you can see problems 1 to Okay, can I expand this a bit more? So you can see 1 to 6 clearly right here. So it says solve the following problems without referring to the worked examples in the lesson because of course they are really straightforward. So here I'll be solving problems 7 and 20. problem 7 and 20. So here you have 1 to 6 all seen clearly. So I'll be dealing with 7. A neuron has 3 inputs. X is 254 and weight W 0.6, 0.1 minus 0.2 with bias B 0.5. Compute the weighted sum. Okay, that's really straightforward. And then maybe I'll even go okay, yeah, maybe I'll go the extra mile to maybe also do the apply activation function, though it's not asked here. So I'll apply maybe at least 2 activation functions. So explain why the bias term is important in a neural network. Okay, then explain why activation functions are necessary in neural networks and all that. So I'll be taking care of 7. I'll go the extra to do activation functions. Then a neural network has 4 layers arranged as follows: follows input layer, hidden layer, hidden layer 1, hidden layer 2, and output layer. Write the mathematical equations for forward propagation through all 4 layers. Of course, so the input layer has all the x's and the weights. So for hidden layer 1 now, you compute the weighted sum, you pass it through an activation function. The result you get, you take it to level 2, and then you do that too. Maybe I should even answer that instead of doing 20. Yeah, I guess I would rather do this. Yeah, I think I like to do 10. So yeah, let me do 7 and 10. Yeah, I think it's 7 and 10 should be good. Then 11, so you see 11 all the way to 13, clearly seen here. And then 14. Okay, 14 to the end right here. So I was supposed to answer this. Write a Python program using NumPy that defines an input. Okay, I think it's better. I don't even worry myself about this. So I think it's good if I do 10 so you can understand the whole concept. I mean, we did something like that before in the notes. So let's go ahead and answer questions 7 and 10 now. Okay, well, I can even let me take a let me snip them together so I don't have to refer to this again. So the focus is on 7 and 10 for sure. I'll just come here and paste. So here we need 7, problem 7 and 10. We don't need 8. We don't need 9. So let's go for that. So I start with this. A neuron has 3 inputs. So problem 7. A neuron has 3 inputs. So X is 254, right? 2, 5, and 4. W is 0 0.6, 0 0.1, 0 0.6, 0 0.1 minus 0 0.2. 0 0.6, 0 0.1 minus 0 0.2. And B is 0 0.5. So we want to compute the weighted sum. So I say to compute the weighted sum, to compute the weighted sum. So we have that will be Z, right? Z is equal to WX plus bias. So Z now is W is 0 0.6, 0 0.1 minus 0 0.2 multiplied by 254, 254 plus B, which is 0 0.5, so that Z now is equal to, well, as usual, 254. It's just one row. We have one row here, so we just write this one. So 0 0.6 plus 0 0.1, 0 0.6, 2 times 0 0.6 plus 5 times 0 0.1 plus 4 times uh minus 0 0.2. All of that added to 0 0.5. So that Z now is equal to 2 into 0 0.6 plus 5 into 0 0.1 plus 4 into minus 0 0.2 plus 0 0.5, like that. So Z now is equal to 1.2 plus 0 0.5 minus 0 0.8 plus 0 0.5. So that is Z equals 1.2 plus 0 0.5. That is 1.7. 1.7 minus 0 0.8, that's 0 0.9. 0 0.9 plus 0 0.5 is 1.4, I believe. No, this is 1 already. So 2.2 minus 0.8. So Z is 1.4. So this is the weighted sum that we are expected to compute. But like I promised, I said I was going to do, I was going to take it further to activation functions. So for activation functions, so we'll start with for ReLU. Talking about ReLU, we have ReLU of Z, that is ReLU of 1.4, which is equal to 1.4 straight up. Then for sigmoid function now, 2 sigmoid function. So we have sigma of Z, because the sigma of Z is 1 all over 1 plus e raised power minus Z. So that means sigma of 1.4 will be 1 all over 1 plus 1 plus e raised power minus 1.4. So we can get the approximate value for that using Desmos. Thankfully, we already have it running. So this is 1.4 here. That is 0.8022. 0.8022. So that's so sigma of 1.4 is 0.8022. So there is an 80.22% chance of predicting the right results. So if you use this, so that's for sigmoid. So let's go and do Tanh. So let's talk about Tanh function, right? Which is also another activation function. So in that case, now we just have Tanh Z, which is equal to Tanh 1.4, I believe. Tanh 1.4. So then we also have that running. Tanh 1.4. So we have Tanh 1.4. So Tanh 1.4. So that's 0. Interesting. 0.8854. 0.8854. So Tanh 1.4 is approximately 0.8854. So well, I mean, this is not probability actually, because this one lies between -1 and 1. So we can't interpret this in terms of probability, basically. Right. Yeah. So we can't interpret it in that term, in terms of that. Yeah. So that's what we have if you're applying the activation functions. So of course here, what I did for ReLU is just 1.4 here. So the answer is maximum of 0 and 1.4 is simply 1.4. So that's you applying the activation functions. So that takes me to question 10. I wanted to do 20 before, but that one is more like story. But let's do question 10, which says a neural network has 4 layers arranged as follows. You have the input layer, hidden layer, output layer, hidden layer 1, hidden layer 2, output layer. Write the mathematical equations for forward propagation through all 4 layers, right? So write mathematical equations for forward propagation through all 4 layers. So imagine this now. We have problem 10. So given a neural network, given a neural network with the following layers, So we have the input layer, we have the input layer, we have hidden layer 1, hidden layer 1, hidden layer 2, and output layer. We have the output layer. So what do we do? So to write the mathematical equation, the mathematical equations for the steps. Okay, for forward propagation, propagation through every layer. What do we have? So for the first step, for the input layer, so for the input layer, of course, what we have at that point is we have, of course, we have X, we can even call it X naught. We have the original input, we have the original weight, and we have the original bias. So if I can use that, so for the input layer, given the the original input, the original width, and the original bias. So what we just have is we can say we have Z1, which is now so W naught X naught plus B naught. And then with that now, we then have the activation function. So we have A1, which is a f of Z1. That's the activation function. So we get A1 from that. So that's for the input layer. Now, so this result now becomes the input for the first hidden layer. So we now go ahead for the hidden layer one. So hidden for the hidden layer one, what do we have? So now we have Z2 equals W1 now. We have W1. So a new set of weights will be given at that level. So the weights will be recalibrated through a back propagation, right? So we have W1 and then W1 together with A1 now, because A1 is what we have, plus another bias, B1. So then we then have A2, which is the which is the next activation, maybe the same or a different one depending on whatever it is we are interested in. And then that will be f of Z2. So that's for the hidden layer one. Then we move on to hidden layer two. So for the hidden layer two, for the hidden layer two, what do we get? We then have Z3, or should I have called this one Z naught? Maybe I should call this. Okay, I mean, it's fine to call it it's all just a matter of notation, so no worries. Let's just leave it the way it was. So you could have called it Z naught, whatever. So for the hidden layer two now, we have Z3 equals a new set of weights now. So through backward propagation, we get a new set of weights, right? Multiplied by A2 plus another bias B2. So that we then have A3, which is the value you get after passing Z3 through an activation function like that. So and then so that we have passed through the input layer, the hidden layer one, hidden layer two, and we go for the output layer. So for the output layer, for the output layer, for the output for the output layer, we then have we now have Z4 equals another set of weights now. That's weight 3 multiplied by the value we got here, A3 plus bias 3. So, and then we then have finally A4, the final prediction we get is equal to, so the prediction you get now, which is Y cap, if you like, is equal to A4, which is a function of A3 that you brought, no, function, which is a function of Z4. Okay, and that's how the equations go in that situation. So yeah, with that, we come to the end of this interesting video talking about how information flows through neural networks. So again, let me show you the question so you can try your hands on them right here. So see them, you have practice problems. You can see all of 1 to 6 here. You can see all of 1 to 6. Then you can see 7. I did 7. I even want the extra mile of doing the activation functions. So you can see 7 to 10 clearly here. Then you have 11 to, you can see all of 11 to 13 clearly here. 11 to 13. Then you can see 14 to 20 right here. 14 to 20. Okay. So with this, we come to the end of this. Let me know how helpful this is for you. And if there's something else you're going to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, why not go ahead and do that right away? Uh, click on subscribe. And of course, hit the notification bell also so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges you find out when you click on join. Like, some videos can be made specially for you as a member and all of that, and more perks that are attached to being a member. Ultimately, don't forget to comment, like, share, so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye. In fact, keep doing AI right too. See you.